Hi everyone, I thought I'll do a quick video of trying to explain what is Diffie Hellman and then the mathematics behind Diffie Hellman. So let's begin. So what is Diffie Hellman? Diffie Hellman is what we call the key exchange. Now imagine you want to do encryption, but in order to do encryption, both parties need to have a shared key to do encryption decryption. But how do you send the key securely across the unsecure network to do encryption? Okay, so how do you send the key securely across the unsecure network? You need encryption. Okay, so can you see the circular argument here? To do encryption, you need a key, but to send the key securely, you need encryption. So you are stuck in a circular argument. Okay, now Diffie Hellman helps to break this circular argument by coming up with using advanced mathematics, okay, that allows them to basically use the concept of two keys, a private key and a public key. So in simplest form, we only pass half a key, the public key, to each other. And through advanced mathematics, we can combine the keys back to the same common key. Okay, so a simplified version of Diffie Hellman at a high level is something like this. Alice and Bob generates a private key. Okay, so Alice and Bob both generate private keys. Alice and Bob both generate public keys. Now the public keys is actually derived from Alice's private key. So both Alice and Bob swap the public keys with each other. Now, through advanced mathematics, Alice's private key plus Bob's public key would yield the same key as Bob's private key combined with Alice's public key. Okay, so basically through advanced mathematics, my private key and your public key will get back the same key. That's crazy. What do you mean by that? Okay, so it's like sorry, I'm a Simpsons fan. So so how is it done? Well, to explain the idea of private key, public key, okay, some high-level explanation uses the idea of a paint job. So there's this idea of common paint, okay, and then there's the idea of a secret paint. You combine the colors together to get the public paint, okay, the public paint, okay, and then combining back with our secret color, we get back the same paint. Okay, so using the paint job example, okay, we learn about, okay, we get a feel of how this idea of public key, private key works. Okay, now today my attempt is to try to explain from using the mathematics behind Diffie Hellman. Okay, now this is a picture borrowed from Wikipedia. Okay, so first, both Alice and Bob will share some agreed on constant value for their mathematical equation. So P equals to 23 and G equals to 5. Both parties agree on some constant value, common constant value for the calculation. So then after that, Alice generates a private key and Bob generates a private key. Okay, now using advanced mathematics, okay, Alice generates the public key using exponent and modulus. Okay, so the number becomes 8. And likewise, Bob uses advanced mathematics, okay, exponent and modulus, to get a number 19. They exchange the public number to each other, the public key number with each other. So Bob's 19 is given to Alice, and Alice 8 is given to Bob. Again, through advanced mathematics, okay, okay, we get back the same shared key of 2. Okay, we get back the same shared key of 2. Okay. Okay, yes, I'm a Simpson fan. What? Still confused? Okay, so let's look at the mathematics behind Diffie Hellman. So as you saw just now, there are two mathematics involved in the calculation: the exponent part and the modulus part. Now, the exponent part is the one that gives rise to the idea of how we can combine my private key with your public key to get back the shared key. Okay, the modulus part is to scramble the public key. Now, because the public key is derived from the private key, okay, without this modulus component, okay, without the modulus component, when people grab the public key, they can reverse calculate back the private key very easily. So the modulus component helps to scramble the public key so that the public key is not reversible. You can't reverse back to calculate the public key, the private key, my apologies. Okay, but okay, it doesn't help with the concept of private key, public key. It's just to scramble the public key. Okay, so because of this, what I'm going to do is I'm going to simplify the mathematics by just focusing on the exponent part. Okay, by just focusing on the exponent part to see how we can use the idea of public key, private key from the eyes of only the exponent part. Okay, so okay, the exponent part. So some of you might ask, what is exponent? Okay, so a quick mathematic refresher course is exponent looks like this. Okay, so personally I call it something to the power of something. So the power is the exponent. So 2 to the power of 4, 4 here is called the exponent. Okay, so 2 to the power of 4, the way we do the calculation is 2 times 2 times 2 times 2. We write it out, equals to 16. Okay, so exponent is to me is the power, 2 to the power of something. Okay, so in the laws of exponents, okay, in the laws of exponent, this is the one that we're going to use. Okay, so if you have a to the power of m and then you raise the power again to n, the mathematics behind it is simply just multiply the power together. So a to the power of m then raised to the power of n again is simply a to the power of m times n. Okay, now to make this clearer, here's an example. 2 to the power of 2 raised to the power of 3 is equals to this. Okay, if you write it out in longhand, this is what it looks like. But okay, so it's actually equals to 2 to the power of 6. So the short observation is simply take the power, multiply them together, you get 2 to the power of 6. Is that okay? So remember this. Basically, when you have a to the power of m raised to the power of n, you simply multiply the exponent together. Now, after this, we take another observation. Now, here we have two calculation. 2 to the power of 2 raised to the power of 3. Okay, so it looks like this in the long form. And the other one is 2 to the power of 3 raised to the power of 2. The long form looks like this. Now, both answer equals to 64 because from the law of exponent, the power concept, you just multiply the power together. So whether it's m times n or n times n, okay, which one comes first doesn't matter because we multiply the exponent together. So whether it's 2 times 3 or 3 times 2, you get back the same outcome. Remember, you get 64. Okay? So this is the simplified version of Diffie Hellman, okay, without the exponent part. So Alice and Bob both agree on some constant value to be used in their mathematical calculation, P and G. Okay, P is used in the modulus calculation and G is used in the exponent calculation. So we're just going to ignore the P part. Okay, so Alice and Bob selects a prime number as their private key. So small a for Alice private key and small b for Bob's private key. Okay, Alice private key, Bob's private key. Okay, now both Alice and Bob generates their respective public key using the formula, okay, g to the power of a, okay, and g to the power of b. Okay, so it's the exponent of your private key. Okay, so a equals to a base value that we both agree on, okay, and then you raise it to the exponent of your private key. Okay, so then we give each other our public key. Okay, so from Alice's point of view, upon receiving Bob's public key, we raise it again to the power of Alice's private key, like this. And from Bob's point of view, upon receiving Alice's public key, we raise it to the power of our private key. Okay, so you have the same key. Looks different, but let's look at the mathematics behind it. Let's put some numbers behind it. Okay, now in my example, g equals to 5. Okay, in my example, let's say g we agree on is 5. Okay, so let's begin. We agreed that g is equals to 5 on both sides. Subsequently, Alice generates a private key. So in this case, the private key is 3. So the public key for Alice would be g to the power of 3, which is 5 to the power of 3. Okay, now from Bob's perspective, Bob generates a private key, Bob selects a private key of 5, a prime number as well, and then b equals to g to the power of 5. So since we agreed that g equals to 5, so 5 to the power of 5 is Bob's public key. So remember, what did we do? We give each other our public key. So from Alice's point of view, Alice received Bob's public key, which is 5 to the power of 5, and then we raise the power to Alice's private key, which is 3. Okay, then from Bob's point of view, Alice's private key is given to us, which is 5 to the power of 3, and we raise it to Bob's private key. Okay, so we have an exponent of Bob's private key. Okay, so from what we learned just now, okay, 5 to the power of 5 raised to the power of 3 and 5 to the power of 3 raised to the power of 5 basically is the same thing. You just multiply the exponent together. So whether 3 comes first or 5 comes first, the multiplication of the exponent 5 and 3 will yield 15. Okay, so the shared key will be 5 to the power of 15. Okay, so through the help of exponent, okay, we get the shared key. I hope you can have a better appreciation of that right now. Okay. Now, for those more inquisitive, for those people that are more inquisitive, okay, I leave this advice for you. the modulus part, as I mentioned, is to scramble the public key so that people cannot reverse back the private key from the public key. Okay, so what is modulus? Okay, what is modulus? Modulus is the remainder. So when you take a number, which we call the dividend, and you divide it with a divisor. So in this example, our divisor is p. Okay, the value p. Okay, it's a shared value that we agree on, p. Okay, and this is the remainder. So, but here's the thing: if you manage to get the value p, which is the divisor, okay, and the remainder value of 1, okay, this value and this value is sent across, okay, you will never be able to find the value of n, the original number. In this case, n, let's say, is the public key. Okay, because if you just have these two pieces of information, you can never be able to figure out what is the dividend, because n divided by 3 give you 1. There are many possibilities. Could be 4, could be 7, okay, could be 10, okay, could be 10, could be 13. Okay, so that's why by adding the idea of a modulus to the public key, we make it near impossible for the hacker to grab the p value, and by just listening to the remainder value, okay, to calculate back the public key. Okay, so this part, don't worry about it. Okay, once you are comfortable with the Diffie Hellman, how the exponent part helps you derive the public key, private key part. Okay, get comfortable with this idea first. Then, if you're more inquisitive, then you explore how the modulus parts help you scramble your public key. Okay, but knowing how the exponent part helps you get the private key, public key concept is good enough. Okay, I hope you have a good day. Thanks, guys.